In a paper published in the Chemical Engineering Journal and just available online, researchers from the Indian Institute of Technology, Kharagpur, Shyamchand Pal and Madhav Das report the synthesis of an metal organic framework, Cu-Prussian Blue, and demonstrate its potential for separations of three different gaseous mixtures: C2H2, C2H4 mixtures, biogas consisting of carbon dioxide and methane, and CO2 capture from flue gases. Indeed, you might argue that Cu-Prussian Blue MOF is a Swiss Army knife category of metal organic framework. Here's the structure of Cu-Prussian Blue as presented in this paper. In this presentation, my objective is to present a tutorial on how to determine the separation performance of Cu-Prussian Blue using the unary isotherm data. This presentation follows the lines of a previous presentation on CO2 capture from flue gases with MOFs on my YouTube channel. We begin by examining the isotherms for CO2 and nitrogen. Measurements of these isotherms have been reported at a variety of temperatures for both gas molecules. And as I have explained in previous presentations on my YouTube channel, fitting of unary isotherms and the spreading pressure concept, I prefer to fit the unary isotherms at various temperatures simultaneously by use of the Langmuir model or the dual site Langmuir model or the dual site Langmuir-Freundlich model with temperature dependent parameters. And I use the Occam's razor philosophy in choosing the proper model to use. And this philosophy is based on the concept that do not complicate things beyond necessity. If the simplest model works, use the simplest model. Only increase the degree of complexity if the data demands it. Accordingly, I fit the nitrogen isotherms with a single site Langmuir model and the CO2 isotherms with a dual site Langmuir model. The parameters are presented here in this table, and for each guest, the isotherms at all temperatures are fitted simultaneously with 3 parameters in the case of nitrogen, 6 parameters in the case of CO2. This fitting I do using the Excel solver. Indeed, for any given example, I spend about an hour or maybe even 2 or 3 hours trying to find the best fit, best in my reading of the situation. It should be the simplest model and it should fit the results with a high degree of accuracy. I refer you to my previous presentations on this topic, but let's proceed with these isotherm fits to determine the isosteric heats of absorption and the absorption selectivities. From the unary isotherm fits for carbon dioxide and nitrogen shown in the previous slide, the isosteric heats of absorption can be determined from the Clausius-Clapeyron equation. This expression can be determined analytically, and these analytic solutions for the QST are plotted here as a function of the molar loading of the gas molecules. Similarly, for the gases C2H2, C2H4, and methane, the isotherm fits using either the dual site Langmuir model or the single site Langmuir model for the case of methane are used to determine the QST for the 5 different gas molecules. These are plotted here, and I invite you to watch my presentation on the fitting of unary isotherms and the spreading pressure concept on my YouTube channel for further background on why I prefer using isotherm fits with temperature dependent Langmuir parameters to determine QST rather than the virial fits that is commonly used in the literature. The unary isotherm fits may be used to determine mixture adsorption equilibrium using the ideal adsorbed solution theory. For a detailed background on the IAST for mixture adsorption equilibrium, I refer you to my YouTube presentation, the IAST for mixture adsorption equilibrium, and this presentation provides the background on the various tenets that need to be obeyed in order for IAST to be applicable. Basically, the partial pressure of any gas component I in the bulk gas mixture P sub I is related to the mole fraction of that component in the adsorbed phase X sub I by this expression in which P sub I superscript naught is the sorption pressure. This expression is the analog of the Raoult's law for vapor-liquid equilibrium. The adsorption selectivity for a binary mixture of components 1 and 2 is the ratio of the molar loadings of the two components divided by the corresponding partial pressures in the bulk gas mixture. And from this expression, we derive that the adsorption selectivity is the ratio of the sorption pressure for component 2 divided by the sorption pressure for component 1. I refer you to my presentation on the spreading pressure concept for further elaboration on the significance of this expression. The IAST calculations for the component loadings Q1 and Q2 and the selectivity S sub adds for 4 different mixtures, a 199 mixture of C2H2, C2H4, 50-50 C2H2, C2H4 mixtures, 50-50 CO2, CH4 mixtures, and 1585 CO2 nitrogen mixtures are shown here. The continuous solid lines here are the selectivity calculations, and these lines with the symbols represent the molar loadings that are plotted on the right y-axis. The IEST calculations show that copper PSB has potential for C2H2 C2H4 separations, CO2 CH4 separations, and CO2 nitrogen separations. The potential of Cu-Prussian Blue MOF for mixture separations is also demonstrated from breakthrough simulations for 199 C2H2 C2H4 mixtures here, and this breakthrough simulations show that it's possible to recover C2H4 containing less than 40 ppm C2H2 in order to provide feedstocks for the ethylene polymerization reactor. The breakthrough simulations here are for 50-50 C2H2 C2H4 mixtures. The breakthrough simulations here are for 50-50 CO2 CH4 mixtures, and these are the breakthroughs for 1585 CO2 nitrogen mixtures. In all four cases, the y-axis is the dimensionless concentrations of the gaseous components exiting the adsorber, and the x-axis represents a modified time parameter, that is Q0 times T divided by M adds, but Q0 is the volumetric flow rate of the gas mixture at the inlet, say in units of liters per second. T is the time in seconds, and M sub adds is the mass of adsorbent in the bed. This is a useful parameter to compare the breakthroughs from different MOFs. In this case, these breakthroughs are used to demonstrate the separation potential of copper PSB for 3 different mixtures.